Okay, hello everyone. Welcome to Compelling Conversations. I'd like to welcome all of our guests and our panelists. So, what is Compelling Conversations? This is an exclusive virtual opportunity for partners, alumni, supporters of physical sciences to learn more about what's going on in the school. And we are focusing on specific questions roughly every month. Motivated by things we're hearing from you that you want to hear more about, and this is one of them today. The title of today's conversation is Anchoring the Unknown, Exploring Fundamental Questions of the Universe. And we'll hear more from our guests in a little bit. Before we get started, I just want everyone to know that we definitely welcome your participation here. If you get excited about some of the research that you hear about and you'd like to support that, it's pretty easy to do that. You can just text the letters PSCC to the number 41444, and any level of donation can make an impact. If you have questions you'd like to direct to the panelists or to me, please go ahead and utilize the Q&A button at any time during the conversation. We'll be monitoring those questions, and I will work those questions in to the conversation as we go along. So before we get started formally, I want to introduce everybody or give a brief introduction to our panelists. So first we have Kev Abazajan. He's a professor in the Physics and Astronomy department and director of the UC Irvine Center for Cosmology. His research focuses on the nature of dark matter, and it works on problems at the interface between particle physics and astrophysics. He's interested in the origin and cosmological impacts of neutrino mass, galaxy formation, high energy astrophysics, and precision cosmology. He has a BS in physics from the University of Houston and a PhD in physics from the University of California, San Diego. Prior to coming to UCI, he's a professor at the University of Maryland as well. Next, we have Paul Robertson, who's an assistant professor in the Physics and Astronomy department. Professor Robertson's current research focuses on using and developing astronomical instruments with the broad goal of finding potentially habitable exoplanets around nearby stars. He holds a BS in physics and mathematics from UNC Chapel Hill and a master's degree and PhD in astrophysics from the University of Texas at Austin. Finally, we have Rebecca Riley, who is a PhD student in the Physics and Astronomy department. She holds a BS in computer engineering and mathematics from Vanderbilt University. Rebecca is actually a third-year graduate student who's studying theoretical particle physics. She's interested in quantum chromodynamics, the strong force, and their applications to nuclear physics. She's also interested in understanding dark matter and dark energy, as well as the identity of intrinsic quantum properties like spin and color. And so with that, I'd like to start the conversation, and I'll try to do less talking from this point forward. So let me start with you, Kev. Today we're talking about deep fundamental questions about the nature of the universe, life in the universe. So a lot of these kind of questions that many of us may ask ourselves when we're looking up at the sky at night. Tell us a little bit about how you got to this moment in your career and what you're focusing on right now. What's taking your time away from some of the cacophony we see around us when you're thinking about bigger pictures?
Thanks for inviting me. It's great to be here with the community like this. I think what's driven me to these kinds of questions, I think, has driven humans for a long time. Ever since people came out of caves and looked up at the stars and thought, "What is that? How did that get there? How did the Earth get here? What is this stuff? What is water? What is fire? What are the stars in the sky?" And we kind of are still asking those same questions, those kinds of questions in the sciences. And I think a lot of what we do in the sciences is trying to, answer questions about the natural world as we see it. And so the nature of the questions are a bit different. Like, we know what powers the sun, and we know that the stars are other suns, and that we're embedded in a galaxy. but some of those same questions are the same ones. Is like, how did that get there, and how did, what composes those things? And so we're still kind of doing that. And for instance, we know that the universe is dynamic now, even though the star field is pretty, as far as we can tell, except for the planets, is pretty static. We know that the universe is expanding, and one of the biggest questions that we have is, why is it expanding as it is, and why is it that there's different measures of that expansion that are finding it to be different when you use early information about the universe from the earliest times that we can measure versus the local universe, the most recent times that we can measure.
Great, thanks, Kev. And I think we'll return to that later because there could be something very interesting going on. And I think some of those measurements, if we don't really understand why the universe is accelerating at its current rate, it could be a clue to something potentially very deep. But before we talk about that, let me turn to you, Paul. Now you're working at a different extreme. You're not focusing on the universe itself and how fast it's expanding. Your focus is on things that some cosmologists might think are really, really close to us, even though they're light years away. So tell us a little bit about what you're doing.
Yeah, that's exactly right. I would say, the extent of my core research really only extends maybe to the closest 1,000 stars. And that still sounds like a lot, but when you consider the fact that the Milky Way galaxy contains tens or hundreds of billions of stars, and the universe is filled with as many of those galaxies as there are stars in our own galaxy, it's a pretty tiny fraction of the overall cosmos. And the reason that I'm so limited is that I'm trying to probe really intensely in fine detail those stars. And what we're doing is we're looking for exoplanets. So the planets that orbit those stars, just like the planets of our solar system orbit the sun. And specifically, I'm interested in finding planets that might be like Earth in the sense that they would be hospitable to life. And a lot of the planets that we've found so far are not really, that you wouldn't put them in that category. They're either outrageously hot or they're so massive that you would just be crushed by atmospheric pressure. And the reason that those are the ones we found so far is those are the easiest ones to detect. And you have to keep in mind, we've only been doing this for 20 years. And so our technology has actually expanded at a pretty impressive clip. And this is something that I'm working on right now. I'm part of the team that's developed 2 different telescope instruments to look specifically for Earth-like exoplanets. And one of them is just wrapping up its first couple years of on-sky operation, and we're just now starting to unlock some of the really exciting science that's coming out of that. And the other one is sort of just now getting its training wheels taken off. So we put it on the telescope about a year ago, got shut down for COVID, unfortunately. This is very much real life for us. But we're finally back on sky. We're observing this week as part of a performance demonstration. So it's really exciting. And yeah, it's a lot going on, both in the broader field of exoplanet science and for me personally.
Great, Paul. We'll return to that a little bit more. But before we do that, I want to make sure we get a chance to hear from Rebecca. Now, Rebecca, you are a particle physicist, but one of the really, I think, fundamentally, amazing things about our universe is that there's this connection between the smallest scales in nature, which is what you study, and the largest scales in nature, this sort of astrophysical, the universe we see around us. I'd love to hear your perspective on that and find out a little bit more about some of the problems and things you're thinking about these days.
Absolutely. I hope that you can all hear me okay. I'm a little further away from the computer. That is exactly where I was going to go. I know Kev does some work on dark matter. Dark matter is a huge focus of the department here and is a big focus of my work. But before I talk a little bit about that, I just want to say how exciting it is to see so many people here that are wondering about the same questions and excited about the same kind of things that we spend every single day on. It's really just great for us to have a chance to talk about these things because it's really fun and we get excited doing it. Like James said, I work on particle physics. It's the very smallest scale that we know of in the universe, smaller than an atom. I'm sure that our very educated guests probably already know exactly what theoretical particle physics is, but when I try to explain it to my family, they kind of remind me how amazing it is that we know so much about something which we can never see. So these are things, the constituents of something like a proton or a neutron, quarks, things like an electron. Are these elemental particles? Are there something smaller? How does the way that these particles behave influence the large scale structure of the universe? Dark matter, as I mentioned, is a huge open question in physics. We see how it works on galactic scales, but from a particle physics standpoint, we know basically nothing. So one of my big features or focuses of my research is on connecting a possible dark matter candidate to another hypothetical particle called a leptoquark. So I don't know if anybody here is familiar with something called Grad Slam, but I actually won last year's Grad Slam talking about this exact thing, so it may sound a little familiar. But a leptoquark is a hypothetical particle that has properties of both a lepton, which would be something like an electron or heavier cousins, and muon are the tau, and also of a quark. So quarks are what make up the baryons, so things like a proton and a neutron. And these are particles which are predicted by certain huge grand unified theories. There's something that particle physicists have been interested in for a long time. But in my research, we're asking the question, well, what if we had a leptoquark and the leptoquark or the dark matter could actually decay into leptoquarks? We then might have the possibility to see particular signals coming from the leptoquarks basically disintegrating very far away from Earth. And so I'm trying to figure out, how would we see that? Would that be possible? Would the signal be high enough? I have a few other projects that I'm working on as well. I'm happy to field questions about one in particular, something called a cue ball. This is a very esoteric type of field theory, but I would love to talk about it, but I don't want to take too much time in this little intro. So I'll hand it back to you, James.
Thanks, Rebecca. So with that, let me remind everybody there's a Q&A button there. And if you have any questions about anything, I guess in the universe, you can ask us. So I guess it's pretty wide open here. There's somebody on this call who could probably say something about it. One of the things I think we've touched on here is that there are a few questions today that I think are sort of umbrella questions that touch on cosmology and astrophysics and particle physics that are, fundamental, outstanding questions that we're still scratching our head about. And Rebecca was talking about one of them, which is dark matter. So why don't we start there? One of the things I think is fascinating about dark matter is that the evidence for it is primarily astronomical. It was discovered initially using telescopes, looking at the heavens and studying how galaxies are moving. And today there's evidence that comes from studying the cosmic microwave background, just evidence right after the Big Bang, and lots of other astronomical surveys are pointing to the existence of this stuff that we don't know about. In fact, something like 85% of the matter in the universe we think is in the form of this dark matter, which is otherwise undiscovered and unknown, like it's nothing in the periodic table. And I think Rebecca was touching on this kind of amazing phenomena that it could be that telescopes, that astronomers discovered evidence for a new fundamental particle of nature, or maybe multiple new fundamental particles of nature that might reveal something deep about the theories that govern the universe itself, maybe even the standard model of particle physics and the standard model of physics itself. Kev, I'm going to throw that back to you because I know you think a lot about these issues. How do you see your role in this picture, trying to connect folks like Rebecca to people like Paul who are building instruments and telescopes, and how we can utilize all of this different expertise to gain knowledge?
Yeah, what's kind of developed, dark matter was discovered about 100 years ago using, for the first initial indications of the kind that we know of today, using clusters of galaxies data. by Fritz Zwicky, and then it was really hammered home by Vera Rubin and collaborators in the 1970s. And since then, people thought it would be something very close to where they expected there to be new physics in the particle physics, which is where what we call the weak particle physics is, that governs nuclear beta decay and also gives neutrinos their forces. And so that's where people thought it should be. And there's been a concerted effort to find it there since the 1980s. And so now we've been on a 40-year trek looking for this signal, and it hasn't been found. So now, there's still some corners there to look, but now it's kind of become a lot more wide open. And so it's kind of a Wild West again in terms of ideas as to what it could be. And so things related to the leptoquark models that Rebecca was talking about could be the direction to look. And so we kind of have to look everywhere. And recently, Paul and I had actually exchanged some emails about ideas where exoplanet formation or exoplanet properties could be used to constrain novel kinds of dark matter. And so it's kind of become, a fishing expedition. We're looking everywhere we can to find out what the dark matter is.
So we've got a couple of questions now that have popped up, and let me field them a little bit, and then I'll toss them back out to the panel to get some perspective. The first question is, what exactly is dark matter? And so I want to make sure that we're not introducing terms that aren't clear right away. One of the really strange things that we've noticed about the universe is, for example, if you look at a galaxy and you measure how fast it's spinning around. In the 1970s, folks like Vera Rubin, who were the first people who really had the instrumentation that was capable of measuring sort of the internal speed of a distant galaxy, showed that the things are spinning around much faster than you would have expected them to be spinning if the only gravity that was there was the gravity of the stars that you could see. And there was evidence then that there's some extra mass there, this extra gravity that wasn't accounted for by normal stuff. And as time has gone on, we've seen more and more evidence that there's just more gravity out there than you would expect from the normal stuff that we see. At roughly the same time, people sort of hypothesized the existence of some additional mass, these particles perhaps that make up this additional matter. And it can't be like anything in the periodic table, because in order for us not to see it, it can't interact with light. It can't, very much at least. It can't shine, it can't radiate light. It has to be more or less transparent, because otherwise we would have seen it. And so it kind of has to be a new kind of particle we've never known about. One initial idea was that it was neutrino, because neutrinos are kind of like that. But now we know that there's just not enough neutrinos, and they're not massive enough to do the trick. And these days we think there's some other new particle that's mysterious, that's maybe kind of like a neutrino or something more exotic of the kind that Rebecca was talking about, that might make up this stuff. And so one question that Mark raised was, okay, hold on a second. You've got a particle that's supposed to exist, but it doesn't interact with anything. How do you detect it? How do you build an instrument to detect something that doesn't interact with anything? And that's true. It's a hard problem. And I think the basic idea, and maybe Rebecca can sort of spin this out a little bit more, is that we hope and we expect that these particles do interact some with normal matter in certain ways, that we can begin to detect it. In much the same way that neutrinos are super hard to detect, but you can find tricks to detect them. So maybe Rebecca, I'll ask you to comment on that. Like, how do you look for something that doesn't interact with anything?
Yeah, that's a good question. And I've been typing to people, so I'm going to keep myself on mute while I'm trying to type in some of the questions. But before I talk about detecting dark matter, huge experimental question. I want to just throw out a little something for all the people that are saying, well, what is dark matter exactly? I mean, this is a really kind of mind-numbing exercise when you really try to start thinking about all the possibilities. And regularly when I go back, I'm from Alabama. So regularly when I go home, I have to spend about an hour with my dad on the couch, and he is trying to grasp dark matter. And he's like, wait, is it like here, like in this room? I'm like, yes. I said, it can actually, it just moves wherever it wants. It's almost like this ghost. I mean, it can go right through you, go through your head, go through your body, it's everywhere. He's like, I always just thought it was out in space. Said, no, it's all around. We don't really know what it is, but basically, as James was saying, it doesn't interact with anything that we can tell so far except gravity. So that does make it very hard to detect. And it is everywhere, but it's also completely harmless. It just kind of goes through you and walls and everything else. There are a couple of ways that people do try to detect dark matter. The primary one, and this is something that I typed in the chat, is something called indirect detection. All of the detection methodologies rely on a hope and prayer that we have that dark matter does interact weakly, but it does have an interaction. If it truly doesn't have any interactions except for gravity, then we are going to have a really difficult time ever detecting it at a particle level, because our best gravitational detections are things like two black holes colliding with each other. I mean, scales so far from particle level that there's no comparison. If it were to interact very, very weakly, there's the thought that maybe dark matter could come in and hit another particle, for example, and that particle, we could see some evidence that something had collided with it. It would start to act a bit differently, maybe send off some radiation. So you have, huge vats of water, places with all these molecules kind of waiting to be hit. That's one of the ways that they're trying to indirectly detect dark matter. So most of these experiments are somewhere deep, deep, deep underground, where we're trying to remove any possibility that the particle could come down and interfere with the experiment. There are some other methods. Direct detection is one. People want to see if you could actually produce dark matter at the Large Hadron Collider. So that was another question. Do I do any work at the LHC? I do not myself, but actually producing dark matter is pretty difficult, just because when you go to the LHC, I mean, if you took a vase and shattered it into 10,000 million pieces on your floor, are you ever going to find every single one? I mean, it'd be pretty hard. And that's kind of what you're looking at when you smash things together at the LHC. It's just going to be difficult to know if we detected dark matter. So it looks like the indirect detection experiments have the best chance.
Yeah, it is a really interesting question. How do you infer the presence of something that doesn't do anything to announce itself? And from an astronomer's perspective, it's kind of going back to what James said. You have to take something that does create a signature of its presence and look for some change in behavior. So, for example, when we look for exoplanets, which technically are dark matter, there's just not nearly enough planets in the universe to account for the mass that's missing. We look for some change in the behavior of the star. We look for it to wobble under the pull of a planet's gravity, or we look for the planet to block some tiny amount of the star's light as it passes between the star and us. And of course, we can extrapolate this on large scales for dark matter. So James already mentioned how stars orbiting within a galaxy are moving faster than they should be, but we also see the signatures of this as galaxies interact with each other. They merge or they form clusters, and we can see the impact on the temperature of the gas that exists between galaxies. All of this points us towards something, some huge amount of mass that we're not yet able to pin down, being there everywhere again.
Thanks, Paul. When you were talking about finding things that are really hard to see, but otherwise don't shine very much, it's reminding me of another really crucial and I think fundamental problem these days, which is, I'll ask it very bluntly, are there planets beyond the sun, beyond the solar system that host life? And finding planets is hard. And I'm not going to tell you how to do that, because that's what you do best. But I mean, I think one of the interesting stories that maybe even relates the quest for dark matter to the detection of planets is one of the first stories of dark matter that was detected by its gravitational influence, and that was the planet Uranus, which you can't see by eye, but was ultimately detected because of the way it was influencing other things that you could see, and so we figured out it was there, and today we're finding lots of other things that you can't see directly by the gravitational influence, like specifically these exoplanets. So maybe you can walk us through a little bit about, this Doppler effect that you're such an expert on, and how that's enabling us to sort of discover these things that otherwise we couldn't see.
Sure. Yeah, it really is this fascinating bootstrap process from sort of understanding that we and all the other planets of the solar system orbit the sun, to then inferring the presence of solar system planets that we can't see by eye, and then moving, understanding that all of those other stars are other suns, and they probably host planets. And so it is extraordinarily difficult to take a distant star and pick out the planets, because a given planet is something like 1 billion times fainter than the sun. And picking out that 1 in a billion signal when it's huddled right next to the star is very, very difficult. And as James alluded to, we do that. One of the ways we do it, and the way that I'm most familiar, is to measure the Doppler effect. So we measure the spectrum of the star. It filters in just like you see. You put it through a prism, and you see the different colors. But in the same way that the pitch of a siren will shift as it speeds by on the highway, those wavelengths of light will shift very subtly as the star moves. And so if a star is surrounded by planets that are all giving tiny little gravitational tugs, then the star will wobble back and forth, and we can measure those frequency shifts. But this is where the cutting edge technology really comes into play, because if you take a star like the sun and put a planet in orbit around it like the Earth, so it has the same mass as the Earth and it orbits in 1 year, the amount that those given spectral lines shift within the spectrum, we record this on a sheet of silicon, just like what's in your iPhone camera. It's just a little bigger and is a little more electronically quiet. And so it's just a lattice of silicon. And the amount that the starlight shifts due to an Earth-like planet, we can count on one hand the number of silicon atoms that starlight moves in between. And so we have to control our systematics to this insanely rigid level to have any chance of recovering that. And so that's really the challenge, is to pin down those most Earth-like planets. We know statistically the galaxy is full of planets. You can go out tonight, and if the weather clears up, you can pick out your favorite star, first thing you see, and rest assured that it's surrounded by planets. But actually drilling down to that answer, is there life out there? Providing a conclusive answer to that, we're going to have to be able to find some of these closest planets so that we can have a chance with space telescopes maybe to measure that 1 in a billion photons and say, well, does this planet have an atmosphere? Does it have a chemistry that would allow life to flourish? And if so, is there any evidence? Again, we're likely to find indirect evidence that maybe some pond scum is undergoing respiration and changing the atmosphere of that planet chemically in a way that would betray the presence of life.
Paul, thanks very much. The level of precision that's required to detect an Earth going around a distant star, reminds me of the level of precision that was required for, the first particle physicists to detect the existence of neutrinos. It's sort of astounding the level of precision and care you have to take. And I'm bringing up neutrinos because of the legacy of Rhinus at UCI, and you're detecting this thing that people have said you couldn't detect. Well, I think in many ways, if you would have asked someone 2 decades ago, are you going to be able to measure the wobble of an Earth tugging on a distant star a star that's 10 light years away, people would have said, you know, no way, right? I mean, they would have said, I mean, just to give you a sense of what we're talking about, you know, a typical star is moving away from the Earth by 100 or 200 kilometers per second, perhaps. Even in the local vicinity, it might be more like 50 or 30 kilometers per second, but like, you know, it's moving fast relative to us. And what you're saying is you have an object that's moving that fast, and then there's a tiny little thing orbiting around it that's affecting its orbit by centimeters per second on top of that larger signal. And that's the, you know, that's the kind of precision that Paul and his colleagues have developed this instrument to be able to look for. And it's really the, you know, it's the holy grail of finding these Earths. It's fascinating. And just to clarify, I think to everyone, you know, we don't think that there's sort of interesting life like the life that we have on Earth on a planet like Jupiter, which is just a big gas ball. There's lots of reasons why. The atmosphere is kind of wrong. There's no rocky surface. The first place that people are interested in looking at are things that are like the Earth, because at least we know that life happened here on a planet like that. And just finding them is just astounding. And the fact that we're getting to the point now that, you know, you're able to do it is amazing. And then of course the deeper question is, okay, well, is there life there? So anyway, I can't help but marvel what these folks are doing. I may have gotten some numbers a little bit wrong there, but it's something like that I think these guys are doing. It's fascinating to me. So there's, you know, we've already addressed, and I think I want to circle back to all these questions because they're so fundamental. Is there life out there? You know, what is dark matter and what is it, and what is it telling us about the makeup of the universe? But we're getting some more questions here on chat that have, I think, motivated some interesting conversation. Kev, what have you seen there that you feel like you'd like to, maybe you can address and then even raise up to your colleagues here for some more discussion?
Yeah, I think there was a question by Preston Bannister and others about kind of like, you know, well, we haven't seen anything, maybe it's not there. And I think that that's a valid question. But you know, when you were talking about exoplanets, we're trying to see something that you cannot see directly through indirect measure, right, through the wobbling of the star. That same kind of methodology has been used throughout particle physics and astronomy to try to find things that should be there, but you can't see directly. You know, the neutrino is, I thought of the neutrino too when we were talking about this, because the neutrino was supposed to be there. And Wolfgang Pauli, who hypothesized it, said, I proposed a particle that can't be detected. But our founding dean, Fred Reines, said, I'm going to try to do it. And it took him decades after the hypothesis of its existence to build the technology to be able to see it. From nuclear reactor experiments. So much of what we do is trying to see something that should be there, but that doesn't mean we're necessarily going to be able to do it. There's another kind of background in the universe that we know is there. It's the neutrino background, and our best guesses for the kind of device that would take to build it with the technology we have requires Earth-sized detectors. And we don't have the funding for that yet. So it's not gonna, we know that isn't gonna happen sometime soon. There's some novel technologies out there that people are proposing. So I think that's what it's gonna take. And that might be what it takes for dark matter eventually too, is to have a new technology nobody's thought of yet to be able to find it. But in terms of the astronomical evidence, it's overwhelming. Like you know that it, you know, when you know that there's a planet around another star before you can directly image it because of its gravitational effects. Same thing with dark matter.
Yeah, I mean, if I could just throw a couple more things out there. I mean, people are asking, you know, in what sense is it overwhelming? Let me just give you an example. So in the 1990s, some experiments were finally launched that could detect and study the glow of light left over from the Big Bang, called the cosmic microwave background. And within the cosmic microwave background, we've actually been able to measure the primordial original density fluctuations that existed after the Big Bang. You can think of these as the seeds of all structure that grew to make galaxies and clusters and things that we see all around us today. The thing that was a little bit unexpected, I guess, about these measurements is how incredibly smooth the early universe was. It was smooth to 1 part in 100,000. And somehow from that incredibly smooth beginning, gravity amplified those fluctuations to produce the incredibly nonlinear and very clumpy universe we see around us today. Virtually the only way that anyone can figure out how you could possibly go from a universe that was that smooth to a universe that's that clumpy today is if you have a tremendous amount of dark matter, something like 6 times as much dark matter compared to the normal matter that we sort of know exists from lots of different ways. And it's virtually impossible to come up with a model. I mean, people have really tried hard to do things like change the gravitational equations in such a way that gives you that cosmological large-scale structure, and it's really, really hard. At first, when people were looking at the speeds of galaxies as the primary motivation for dark matter, there were a lot of ideas about maybe changing gravity and the gravitational force law. And a lot of those in principle could work. But when you can combine it with the large scale structure of the universe and observations from the cosmic microwave background and things like that, it really, it's almost hard to, it's really, really compelling evidence that it's there. And believe me, if I could come up with a way to explain it without that dark matter that was fruitful, I would certainly do it because, it'd be kind of a big deal. And a lot of people try, and it's really, it just looks and smells like dark matter in so many different ways. So yeah, I'll try to stop talking about dark matter because that's what I work on too. Let's move on now. I guess I'm interested in kind of throwing something back at the panel. What are some of the other deep questions? I guess I want to sort of end up today by talking a little bit more about life in the universe and what that even means, because I want to, and I'd love to hear some cosmologists and particle physicist perspectives on that, because it's just interesting to hear. But is there a big question that we haven't talked about yet? We've talked about exoplanets and life a little bit. We've talked a little bit about dark matter. Maybe is there another deep question, maybe having to do with dark energy that we could talk about? Kev, you had talked about this earlier. Maybe you want to discuss that briefly?
Sure. So dark energy, and I think there was a question among the list was, is there any relation between dark matter and dark energy? And there might be, but really the joke is the only real necessary commonality is that they're dark. So they're, so if dark matter is 5 or 6 times as much as the normal matter, turns out dark energy is twice as much as that. And so it's, if you're on an energy accounting scale, 95% of the universe is matter or energy that we do not know. And the reason we know that dark energy is there was that in 1998, it was discovered that the universe is accelerating, including by astronomers at Berkeley and Harvard. And now it seems, we see that the universe is accelerating from those observations, and the only way to get that acceleration is to have a new component of the universe that is smooth and non-radiating, that is not giving off light, and everywhere. And so it's kind of a zero energy level would do that. So it just pervades space, and so that's why it's called dark energy. But once you have it there, then the question is, what is it? And so there's a big effort to try to find out how it's affecting that expansion rate in a very precise way to get an accounting for that expansion, to see if there's some evidence for it to be dynamic. And right now we're at a point actually where it does look like something weird is happening. And that is that the expansion rate now seems to be too fast relative to what it should be, given information from the very early universe. And that's driving a lot of interest in new physics. And so I'm working with a postdoctoral scholar here, Mauro Valli, and a student at USC on looking at how the expansion rate could be an indication for new new dark energy, basically. So dark energy that's sometimes called phantom dark energy. So it has a very weird equation of state.
Thanks, Kev. Oh, go ahead, Paul.
Well, I was going to say, I think dark energy is really interesting as well. And as it turns out, the exoplanet detecting instruments that I and my colleagues are spending effort working on can actually potentially help answer some of this question. And I'm not an expert in how dark energy works or the leading theories to explain it, but I think at least part of it could be better understood if we were to discover, say, that some of the fundamental constants that we think are constant might be changing over the history of the universe. And so one science case outside of exoplanets for the technology we're developing is to look at objects in the very distant universe. And of course, the finite speed of light means that when we look at more distant objects, we're looking further back in time. And there are certain relative line positions. There are pairs of spectral lines that are seen in these objects that if, say, the fine structure constant, which encodes fundamental physical constants like the charge of an electron and the speed of light, if that's potentially changing over many billions of years, then these instruments that we're building are actually stable enough to measure the positions of these lines drifting as a consequence of that over time. So that's a potentially really exciting long-term outcome of these instruments that we're building that have really nothing to do with the purpose that we're building them for.
Yeah, I mean, I think that I love this part of the conversation too, because I think dark matter is a really interesting kind of shiny thing to talk about. A lot of people want to ask a physicist about dark matter, but there are so many other interesting questions that we think about that don't get as much attention. One thing that I've been interested in and haven't gotten to spend a lot of time on yet is the theory of information from a particle physics point of view and from a quantum point of view. This was something that I believe it was Wheeler worked a lot on at the end of his life. What kind of is the universe fundamentally information? When we have things like black holes, this was something Hawking worked on. Do they destroy information? Well, it turns out that they don't, but then you get all these problems along with that. Where does, these things that almost, it seems like the universe has some knowledge that we can't really figure out what's going on. Things like the EPR paradox, that's a quantum phenomenon. So all of that is very interesting. I also have some interest in working on these kind of geometric field theories. They're sort of a mathematical concept with which we might understand fundamental physics better. There's a lot of very surprising connections that people have found and some of these super esoteric field theories that I'm curious, can we apply that to something like our field theory with the standard model? So if you are ever curious about that, I know that you all are supporters of the school, and I love to talk to people that are interested in physics and like to support UCI. So I can leave my contact information in the chat if those are things that kind of you'd be interested in learning a little bit more about. But I just wanted to throw out there that there's very cool questions in addition to just dark matter and dark energy.
James, if you're wanting to tie this to the presence of life in the universe, these questions of dark matter and dark energy are really interesting when you put it in the concept of a potential multiverse. So if there are many universes out there that have different ratios of regular matter, dark energy, not all of them are likely to be amenable to life ever taking hold. And so there's this interesting sort of philosophical connection between the type of universe that we're in now and even the possibility of life existing and then observing its own universe.
Yeah, I mean, one of the things that if you think about the observation that the universe began very smooth, had we been born in imagine there's lots of universes, we don't know if there are, but if there were, imagine we had been born in a universe without dark matter. It's almost certainly true there'd be no galaxies. So, and without galaxies, you don't have stars. And, as far as we know, without stars, there's no life. And so it would be, hard to have a universe like ours, to have any life in any way like we understand it if there were no dark matter. And so that's kind of crazy if you think about it. But as far as we understand that, that is the case. And so the way all these things connect is sort of fascinating. I wonder actually, Paul, let's start with you, but I'm interested very much in how other people are thinking about this question. There's sort of the big question, right? The big question with life is not necessarily microbial life. I think that a lot of questions that people are asking about is there intelligent life? Is there a life that we could communicate with in some way? And this is a much harder question, but one way I like to think about it, I wonder how you think about it. We know on Earth that life began, we think, pretty soon after there was liquid water on Earth. Certainly 4 billion years ago, we probably had some kind of very simple life on Earth. And then it took about another 4 billion years, within the noise, for anything that like us to arise, who were sort of self-reflecting, that might eventually build a telescope. Is the typical timescale 4 billion years? Would it normally take 20 billion years, of which case we're way ahead of the curve? Or are we late to the game, and is it more like usually only takes 1 billion years, and therefore we would have expected there to be lots and lots of civilization out there? How do you think about that question, Paul? I'm sort of getting to the Fermi paradox, but it's how do you think about that question, and how does it drive you, or is it somewhere in the back of your mind?
Yeah, this basically keeps me awake every night. It's hard to answer the question that you posed, which is how long does it take for intelligence to develop when we only have a sample size of one? Of course, the related question is it even necessarily evolutionarily advantageous to develop intelligence? A shark made its way to the top of the food chain without developing technological sophistication just fine. But the other way I think of it is this: we've discovered stars that are 11 billion years old. They're as old as the Milky Way galaxy and billions of years older than the sun. And we can't say anything about life around those stars yet, but we have found planets orbiting those stars. So we know the planets and potential habitats for life started forming early. And the other number to keep in mind is that if even one spacefaring civilization decided to set out and colonize the galaxy, it wouldn't take billions of years. It would take millions, maybe 1 billion tops, for one civilization to visit every star system in the galaxy. And so I think it's quite likely that the entire galaxy is full of maybe not squishy organic beings, but some types of robotic probes that are moving throughout the galaxy and just cataloging data and sending it home. And it's totally possible that that type of probe could be sitting in the solar system and we would be completely unaware of it. You think about what the largest spacecraft we've sent out into the galaxy and how those compare even to small asteroids. It's easy to hide stuff in the solar system. And so the fact that nobody's landed on the White House lawn and announced themselves yet doesn't really tell me anything about whether or not there are other intelligences out there. And even the potential rarity of intelligent civilizations doesn't matter too much to me when you only need one.
Paul, I actually have a follow-up question for you. So I read recently a paper. I don't know if you'll have heard of it or not, but it was by some evolutionary biologists, and they posited that there were a certain number of steps in evolution required for us to be intelligent, and that based on their analysis of the statistical probability of moving from step to step, that life on Earth had basically evolved at a much faster rate than statistically was plausible. And that when they looked at statistically how long it should take to go through these steps, oftentimes that was longer than the lifespan of a star. And so their analysis of how much intelligent life there was potentially in the universe was dramatically decreased from what other colleagues were saying, just from kind of estimates based on Earth. Do you know about this paper? Do you have any comments?
I haven't read that one specifically. I think that's probably something you could put into a broader category of analyses related to something you might call the great filter, that there's some step past which you evolve and you are a technological civilization such that could be detected by other star systems. And the presence of a filter would imply that most life forms don't get there. Now, in terms of a stellar lifetime, you have to remember that the sun is not a typical star. So something like 75% of the stars in the galaxy and in the universe are stars that have less than half the mass of the sun. And they go through their nuclear fuel much slower, such that their what we call main sequence lifetimes are not billions of years, but trillions of years. It'll be many times the age of the universe before these stars burn out. And so if you can form habitable planets around those stars, then there's plenty of time for intelligence to develop and again, move into being a spacefaring civilization. Now, it may very well be still that we're the first. That's a disappointing answer if you're looking for other intelligences, but it's certainly a possibility.
Thanks so much. James, I don't want to hijack this, but there was one question. I know that we're kind of getting low on time that I want to make sure that we got to from Jacqueline. And she directed it to me, but I think we can all answer this question. She said, is the kind of thinking that a theoretical physicist does very rare? When did you first realize or understand that you were able to do this type of thinking? Is it something an elementary or middle school teacher could look for in their students to guide those who have this ability? So I think it would be great if we could all kind of maybe talk about when we realized that we wanted to get into physics and how we can support young people that, that's their dream. So for myself, I was always really fascinated by space. So I think that an elementary school teacher or a middle school teacher could have pegged me instantly for a potential physicist. I mean, I figured out that the public library in our county had this feature where you could request books and then they would like put them on this little hold shelf for you. And so once a week I would go in there and, come out with a stack of books about this big. And the sense of curiosity is something that I hear a lot of my colleagues talking about, something that they had when they were young. They were reading all the time. They were just like a sponge, basically trying to soak up as much knowledge as possible. That did not directly translate for me, however, into becoming a physicist. As James mentioned, I actually was an engineer in my undergrad. I knew that I liked science and math, but this, as stupid as it sounds, I truly didn't realize that people could be a scientist for an occupation. And so I had the, not bad advice at all to go into engineering. And I would always have a stable job and plenty of money. But when I was talking to a physicist that I knew through a completely different channel, we were having a conversation about CERN, which I had gotten the opportunity to visit. And after our 10 or 15-minute conversation that was so delightful, I had an epiphany moment. And I just thought, man, this stuff is so cool. I just wish I could think about this and talk about this all the time. And I mean, I was like, hello, you can like go do this. This should be your life. So that's kind of my story, but I'm interested in James, Kev, Paul, you guys too.
Let me deflect to Kev. Let me ask Kev.
I think, so it's kind of a similar story in that I grew up in Houston, Texas, or suburb right outside of Houston, near the Johnson Space Center. And I was like, went on third grade field trips to the Johnson Space Center. And I thought, this is cool. Space is awesome. I want to do space science. I don't know what they do in space science, but I want to do space science. And so that developed into a little bit older. I read some popular science books on cosmology and kind of got it in my head that was something that would be cool to do. And I think having a good preparation and some talent at math and physics that I was able to continue. you know, and I think this is something that I wanted to tie in a little bit in that there's some kind of knowledge that's useful in that you can take it and build a better widget and make some money off of it. And there's some kind of knowledge that has value in itself. And that kind of thing has driven me more, you know, personally in trying to get this kind of knowledge. Like if there's life on other planets, that it would be amazing to know. And that has value in itself. And if there's, you know, if, you know, what is it that causes galaxies to form and solar systems to form? That's also kind of what has driven me.
Thanks, Kev. Paul, I want to hear from you.
Sure. I remember when I was really young, I saw a documentary on the Voyager probes, which somebody actually mentioned in the Q&A. And I just thought it was fantastic seeing these close-up images of the outer planets. It was just so alien and majestic to me. And around that same time, the first exoplanets were discovered. And I remember just hearing about this in school, and everything sort of clicked together, like from very early age. That's what I want to do. I want to be one of these planet hunters. And I'll echo what Rebecca said. I think encouragement is such an important part of this. And my parents really supported that interest. I remember coming down for Christmas one morning and there was a telescope sitting under the tree. And my dad would pull me out of bed at 5 a.m. to go see the moons of Jupiter or something. And I think there's a lot of academic literature, pedagogy literature that suggests that certain people, you know, women and people from underrepresented socioeconomic groups don't get enough of this for whatever reason. And so if you have an opportunity to take a young person under your wing who has this interest and potentially the drive to be one of the people who's really great at this, but has been told somehow that it's not for them, then that's one of the best things you can do, both for your community and for your field, is to encourage that and help them find a path where they can make contributions.
Thanks, Paul. I mean, I endorse that idea 100%. I think from my own perspective, I'll sort of give you a two-part answer. If I really think about it, at some point in my life, you know, maybe when I was in high school, I decided that, you know, I was just sort of thinking about the world in a particular way. And I thought, you know, what is the thing that the humans do best compared to all the other species? And I thought, well, they think. And they ask questions about that transcends their tomorrow. So I want to do the thing that we do best. I want to answer these questions and work on that. But at the same time, I think had anyone at any point said, you're not smart enough to do that, or if at any point anyone had given me any negative feedback, I probably would have quit, because I already thought it was probably too hard for me anyway. And at no point did anyone ever say that to me. You know, they always said, well, come sit down. And I just imagine, had I just been coming from a different background, maybe that wouldn't have happened. And then I wouldn't be able to do what I do now and maybe contribute whatever way I do contribute. I think it's really important to cast those nets broader and invite as many people in who are passionate about it as possible. And you know, maybe people initially get excited thinking about exoplanets, but then they go into sort of, I don't know, quantum computing at some point, and then, you know, build the best computer ever. And then with that computer, they cure cancer, right? I don't know what the trajectory is going to be, but I think inviting more people in to ask deep and profound questions, I think the better it is for all of us. And with that, I think that might be a good point to end on. I want to thank my three guests here today. What a great group. And I have to say, Rebecca, I'm so glad you were able to join us. It's so exhilarating to have one of the PhD students, you know, one of the future of science here. You know, this is the epitome of what great research universities do. They not only do core research with their faculty, but they train the next generation of scientists. And we're seeing this sort of some sense of the breadth of questions that we're all asking. Please, if you're on the call and you have more questions for us, go ahead and shoot us questions. Happy to answer them. This is going to be posted on YouTube sometime in the next, I think, 48 hours, and you'll get a note on that if you want to watch it again. So thanks, everyone, and we'll see you next time with the next compelling conversations. Bye-bye.